Hey everybody, we're going to cover some questions from section 3.2 in the practice of statistics. Let's start with number 55. So we have this situation where they are trying to predict free skate scores using short program scores. So X is the short program and Y is the free skate. And they have 24 skaters and they made a regression. They lovely gave us the regression and also the S and the R squared. So the first thing, question A, asks us to calculate and interpret a residual. So let's keep in mind what a residual is. It is the actual Y minus the predicted Y. So I need to find the predicted Y. I've had a few students ask me like, well, how do I know the prediction? Prediction comes from the least squared regression line. So up here, if I am trying to use the information I was given, remember the short program score was X. So I'm going to have negative 16.2 plus 2.07 times X, and in the thing it says that we have a score of 78.5 as the free skate, or sorry, the short program. And so for Y hat, I end up getting 146.295. And I'm going to now do the actual score. So again, like in the problem in part A, it gives me the actual score. So I have 150 minus 146.295. That's the actual minus the predicted. That gives me 3.765. Then it asks me to to interpret what this means. It says calculate and interpret. That's really common. Make sure you look out for that wording. I need to say what that 3.765 is. And so because it's positive, that tells me that our actual score was higher. So let's see, here we go. Unichem's free skate score, so that's the Y context, was 3.765 points higher than what was predicted by the least squared regression line. Part B asks if a linear model is appropriate for these data. And looking at the residual plot, I don't see any leftover pattern here. There's no pattern actually happening in the residual plot. So I would say yes, a linear model is appropriate. Because there is no pattern in the residual plot. The next two questions ask us to do some interpreting. So we should use those scripts that I have given you before. If I want to interpret the value of S and then interpret the value of R squared, S was 10.2. So your book says it one way, and it is good, kind of the way that the script that I had given you guys before, said something along these lines. So the actual Y context, which in this case is free skate score. So the actual free skate score is typically about 10.2 points away from the predicted number by the least squared regression line. So that's like about how far away the prediction is, typically, meaning like it's an average distance. And then let's look at R squared. So R squared was 0.736. Okay, about 73.6% of the variation in free skate scores is accounted for by the least squared regression line relating free skate scores to short program scores. So that's the really typical interpretation, like the script that you can use for R squared. It's not 73.6% accurate. It's not 73.6% correct. It is that 73.6% of the variation is accounted for by the least squared regression line, which we know based on that activity we did before. That means that the least squared regression line is going to make predictions 73.6% better than just using the average Y for your prediction. Okay, this one's a little bit hard to see, but this is using one of those outputs. So it says that exercise 13 gives data on the number of breeding pairs of merlins in an isolated area in each of 7 years and the percent of males who returned the next year. Talking about those birds. The data shows that the percent returning is lower after a successful breeding season and that the relationship is roughly linear. The figure below shows a mini-tab regression output for these data. Y'all, honestly, this is probably more like what the APU test is going to look like. They'll probably use something like this instead of having you actually calculate the linear regression. So the key is these two numbers here when they ask for the least squared regression line. So part A, what is the least squared regression line for predicting the number of males that return from the number of breeding pairs? Let me use my highlighter here. This first number, the one that's under constant or next to constant, that's always the y-intercept. So I'm going to have y hat equals 266.07. And like that's the y-intercept. And then the number underneath it is the slope. And that is negative 6.650x. Please remember that you need to actually define what these variables are. So this is where y hat is the percent of males that return. And x is the number of breeding pairs. And I just kind of pulled that from the original problem. All right, B, what percent of the year-to-year variation and percent of returning males is accounted for by the straight line relationship with number of breeding pairs the previous year? Okay, so this is, I recognize some of those words, especially after we just went over number 55. This is basically just asking you for R squared. Like, what was the percent of variation accounted for by the least squared regression line? So the answer to part B comes from right here. I'm underlining it. So that was 74.6%. Notice that I just used the one that says R squared or RSQ. I don't use the one that has the ADG next to it, ADJ, I'm sorry, ADJ, because it's the other one is the adjusted R square, which is not something that is appropriate for us to use. We're always just going to use R squared. And then the last question says, use this information to find the correlation between percent of males that return and the number of breeding pairs. How do you know whether the sign is positive or negative? Okay, this is really interesting. I find it interesting. So we have R squared, it's 0.746. So to find R, I need to find the square root of that. And when I do that, that gives me 0.864. But something is off here. I need to change the sign. So I get whether it's positive or negative from the slope. So back up here, I'm underlining it in red where I wrote part A. Notice that the slope was negative. So that means that this was supposed to be negative. Like I'll put a negative on the outside of the square root sign and a negative on the outside of my R. And I'll just make a note. It was because it had a negative slope. So the slope's sign and the R's sign should match. All right, lastly, D, interpret the value of S in this setting. So it gave us S. And we actually just did this not long ago. We can look back over here, in fact, and see the actual something is typically this far away from the predicted number. So in this case, I'm talking about the percent of males returning. So the actual percent of male Merlins returning is typically about, and that is this value up here, that's 7.76. Typically about 7.76% away from the number predicted by the least squared regression line. Why did I put a percent here? This might seem a little confusing. The units on my Y's was percent. So like on my problem I did here, you'll notice that I said 10.2 points away because it was talking about a score. Here it said it was actually talking about percents, the percent of male Merlins returning. And so the 7.76 was actually a percent. The next question was question number 67. Do beavers benefit beetles? Researchers laid out 23 circular plots, each 4 meters in diameter, in an area where beavers were cutting down cottonwood trees. In each plot, they counted the number of stumps from the trees that were cut by beavers, and then the number of clusters of beetle larvae. Ecologists think that the new sprouts from stumps are more tender than other cottonwood growths, so beetles prefer them. All right, so if so, more stumps should produce more beetle larvae. And here was the data. Can we use a linear model to predict the number of beetle larvae from the number of stumps? If so, how accurate will our predictions be? Follow the 4-step process. Okay, so you're probably all were looking at this, at least in my class, saying, what is the 4-step process? I have not really focused on the 4-step process yet. It is a process. It is helpful. It's something that's good for free response questions. Just like a quick overview. It's state, plan, do, conclude. So stating is kind of like, what is the question? Plan is, what are you going to do to find it out? Do is actually running it, and then you make your conclusion. I don't know that that's necessarily super important for us right now, but we're definitely going to be doing state, plan, do, conclude later in this course for a lot of our free response questions. But this one I feel like is relatively straightforward. We could restate the question if you wanted to. So stating would just be stating the question. Planning, okay, let's talk about what we would do to actually figure this out. Is a linear model appropriate? I think there's 2 things we could look at. We could look at the graph and find the correlation coefficient, R. But you know, that's a little deceiving. So a really good thing is to look at the residual plot. So that would be our plan. We want to do a linear regression and find the residual plot and see if there's a pattern. So what I did was I went ahead and typed this information into Statlet so that we could take a look at it. So I have stumps here, beetle larvae here, and I'm going to hit begin analysis. Okay, there it is. You notice that like for one stump, there was a lot of variation. 2 stumps, 3 stumps. So this is kind of like a funny looking scatter plot because like we have whole numbers on the X's and then multiple values for the Y's. Definitely not a function, right? But that doesn't mean it's a linear model isn't appropriate. So I'm going to go ahead and calculate the correlation. Okay, so 0.91 is like, that's pretty high, but we need to see if there's a pattern. So I'm going to, when I click calculate least squared regression line, it creates a residual plot for me. And if we expect there to be numbers like stacked like this because that's how our line was. But notice there doesn't really seem to be a pattern here. There's like some above, some below, some above, some below, 1 below, some above, 2 below, you know, like there's no curve, there's no distinct pattern here. So I believe that it actually is appropriate for us to use a linear model. And the R also helps with that too. So let's say, the residual plot doesn't show any obvious patterns. And R equals 0.92, which shows the linear relationship is strong. So the linear model is appropriate. Okay, so don't worry about the 4-step process. I think this is fine for now. And 69 was one that I actually assigned in a later assignment, but I thought it would make sense to go ahead and go over it now. We are going to have to make a scatter plot right away, and so I'm going to need to type all of these things in. Now notice that the subject numbers is not actually what I'm including in the scatter plot. It specifically said make a scatter plot with HbA as the explanatory variable, and down here it said the FPG, which is the fasting plasma glucose, is like what they're trying to predict. So I'm going to type all of this stuff in a Statlet and describe what we see. Let's read the problem for a little more context. So people with diabetes measure their fasting plasma glucose, FPG, measured in units of milligrams per milliliter, after fasting for at least 8 hours. Another measurement made at regular medical checkups is called HbA. This is roughly the percent of red blood cells that have a glucose molecule attached. It measures average exposure to glucose over time period of several months. The table below gives data on how both HbA and FPG for 18 diabetics 5 months after they completed a diabetes education class. All right, so describe what you see. That's kind of vague, but to me that says that we're supposed to be describing the relationship between the two of them, probably. And so I'm going to go ahead and say we should do CDOFs here. So let's take a look at it. I went ahead and made the scatter plot. There it is. Sometimes I think it's helpful to calculate the correlation so you know how strong it is. So like this is not really strong. I would call it moderate. It's really close to 0.5, so I would call it moderate. So taking a look at this, I can see there's a positive relationship, positive, linear, moderately strong. There do appear to be some outliers, maybe this subject out here, and then probably this subject out here. Like if those weren't there, then the rest of these would be a lot closer to a line. So I can see that was 10.7. And which was subject 15, and this one, the 19.3 one, that was subject 18. So let me just write this down. So remember CDOFs, the C stands for context. So I need to have something in there about context. The scatter plot showing the relationship between HbA and FPG shows a moderate positive linear relationship. Notice that that sentence just covered the context, the direction, the strength, and the form. It just hasn't covered outliers yet. So I need to say there are possible outliers. To the far right, which that was subject 18. You can see that right here because that was the 19.3, that one right there. And near the top of the plot, which was subject 15. You can kind of describe where they are, or you could give the exact values if you wanted to. All right, so that's how I described what I saw. Please, guys, on the test, if it asks you to describe the scatter plot or describe the relationship, so sometimes it'll just say describe the relationship. So I could have just said the relationship between, I couldn't, like right here, I could have taken out the scatter plot. So the relationship between these is, you know, a moderate positive linear relationship, and that would be totally appropriate. Okay. Part B, subject 18 is an outlier in the x direction. What effect do you think this subject has on the correlation? What effect do you think this subject has on the equation of the least squared regression line? Calculate the correlation and equation of the least squared regression line with and without this point to confirm your answer. Interesting. So let me go back over to the scatter plot here. So for a moment, I need to do some imagining, and it's hard for me to do this. I might take a picture of it so that I can put it on the screen and actually draw on it. So that's really large. Okay, so I'm going to have to kind of imagine what's happening here to the best of my ability. So I'm going to draw a line. I think that with this point, the line is probably like something like this, maybe. And if that point was gone, I'm going to do a different color. If that point was gone, I kind of honestly would imagine the whole line tilting a little bit. Like, wow, that's a really fat line. I imagine that it will tilt away from this point. Like, it'll probably tilt up this way. That's probably not exactly right. Okay, I'm really just guessing here. So y'all are we're just gonna test and see if I was right or not. So I think that R will get stronger because that was an outlier. So I think the correlation is gonna get higher. I think the slope is gonna increase, and I think that possibly the y-intercept is gonna decrease because it's gonna have like tilted, which will bring that purple line down. Okay, moment of truth. Let's see. So I need to go back up here. Subject 18 was the last point. So if I take this last point off of both the x's and the y's, that gets rid of that point. But I didn't look at the R before in the line. Whoops. Okay. I'll go ahead and hit begin analysis, and then I'll add those back in. Okay, so it kind of like, it zoomed in a little bit more, so it looks a little bit different. Okay. So this is the correlation and the least squared regression line without that point in it. And then I will redo it with the point in a moment. Okay, I've added that point back in. And now I'm here. Let's take a look at the correlation. Ooh, I was wrong. It was actually higher with that point in there. I guess with it out there, this linear, I guess it is kind of in the linear pattern. I should have thought about that. The line would have been like this, like closer to the linear pattern. Let's take a look at the least squared regression line and compare these. It looks like I was just wrong. The slope did decrease. No, yeah, okay, yeah, this is the new one. This is the old one. Nope, let me back up. This is the one down here is the one that has the outlier in it, and the one up here is the one that doesn't. So notice that the slope did increase from 10 to like 12-ish. The y-intercept did decrease from here to here. So that was what I predicted, that the slope would increase and the y-intercept would decrease. But I was wrong about the correlation, and for good reason. I just didn't think about it. I didn't realize that that outlier would have been in the pattern. So because that outlier would have been in the linear pattern, the R is actually going to decrease. All right, sorry, it takes a minute to get all this lined up. So this one was without, this one was with. And the question was kind of asking what would happen if we took it away. So the outlier strengthens the R, which makes it closer to 1. This is positive. Removing the outlier increases the slope and decreases the y-intercept. All right, and there's our proof that it actually happened. Part C is kind of similar. It says subject 15 is an outlier in the y direction. What effect do you think the subject has on the correlation? What effect do you think it has on the least squared regression line? And it wants us to calculate the before and after again. So I'll pause when I'm doing a little bit of this work so that it's not quite, so it's not quite as much of me typing and being slow. Okay, I took out subject 15. That was 10.7 and 359. So I'm going to begin the analysis. It looks like this. I would predict, I guess going back over here to this one, if I am imagining, I'm going to take the purple one out now. I'm imagining that this black line is the least squared regression line as it stands. If I were to take this point out, I don't imagine that the slope is really going to change very much, but to me it seems like the whole line would like shift down. That's very dramatic, but because that outlier's in the y direction, I think it's pulling the least squared regression line up, and so if I take it away, it's going to make the least squared regression line go down. Probably not that dramatically, but let's see what happens. So the correlation, remember this is down here with all the outliers, this one right here, this is the least squared regression line and the R value when all the outliers are in it. So right now it's 0.48. I'm imagining that taking this away is going to make it better, make R stronger, because it this is so far out of the pattern. So if I took it away, it would make R stronger. So if I put it in, it's making R weaker. It's making it closer to 0. Let's take a look and see. Let's run some analysis and see what happens. So without that high point in there, my R is 0.56, which is indeed higher. And then I have my point here, and it does look like some things have changed a little bit. So I'm going to take a picture of it and put it over here so that I can compare these two. Okay, so notice with the outlier, the R is smaller than without. Also notice that it looks like something strange happened here. It looks like it did tilt a little bit. This is not making much sense to me. Because that says that the y will go up. So really, and I mean this is correct, I did do it correctly. I would have anticipated the y-intercept to decrease and the slope to stay pretty much the same, but it looks like it kind of actually tilted a tiny little bit. It made the slope less and it made the y-intercept more. So it tilted it ever so slightly. So I'm going to say what it actually did. The outlier in the y direction decreases the R. I'm going to say weakens the R, making it closer to 0, because it's not in the pattern. I would expect it to affect the y-intercept more than the slope, which is somewhat true. I can talk about what actually happened here. The outlier made the y-intercept slightly less and the slope slightly more. Because this was with the outlier and this was without it. So I would say that the x one did what I expected it to do, and the y one was a little surprising.